date in 2011. And because, well, we'll be talking more about state death records shortly, but for now, I'll just say that these are one of the best sources of death data that we have. So because of this rather glaring omission in them since that time, there's some consensus that this death master file is just not sufficient on its own for purposes like we want to use it for, where we really want to get relatively comprehensive death data on a given set of individuals. So the Centers for Disease Control and Prevention, they also have a national collection of mortality records, and theirs is called the National Death Index. So theirs is generally recognized to be the most comprehensive national collection of death data that we have, and it can be accessed for research purposes, but you don't get a full copy of this data set if you're trying to get access to it for research. What you'll do is you'll submit the identities for all the records you have that you're interested in. CDC will match them to their death records and then send you back the matching results. This is also not free, it's done at a cost. So I'm simplifying their cost structure here for the purpose of illustration, but roughly speaking, it's going to cost you about 20 cents per record that you're trying to match with them for a given query. So if you're working in a smaller scale study, maybe you only have to match about 5,000 records, that's around $1,000, and maybe that's something you can budget for. But in cases like ours, where you're getting into a healthcare system that has millions of records, then you're talking about hundreds of thousands of dollars. And on top of this, that's just per query. So for us, we would want to be keeping up-to-date death data on our patient population. So we would need to resubmit this query regularly, and we would be incurring this cost every time that we do that. So the National Death Index quickly becomes cost prohibitive for purposes like ours. So where does that leave us? So healthcare systems and research studies for whom Death Master File and the National Death Index don't really work out, we're sort of left to come up with a custom solution, and that's what we've done here. So what we've done here is actually sort of skip that middle step of the CDC. So they actually derive their National Death Index data from records they get from the states. And it turns out we can actually go directly to that source state data ourselves. Because conveniently in our case, UNC Health is a state healthcare system, so its range is nicely circumscribed to the state of North Carolina. And US states tend to have nice systems to keep comprehensive records on mortality data. So UNC Health, the Information Services Division, has an arrangement they've worked out with the North Carolina Department for Health and Human Services, where we're able to obtain summary files of those state death records. And those get updated on a monthly basis and then delivered to us on that same timeline. So this is really the first big challenge overcome here. So we have access to a source of much more comprehensive death data that we should be able to use to fill in all of what's missing in our EHR. But the next challenge is, how do you determine when a person from the state death records is the same person as a UNC patient? And if you've never worked with data linkage, this could seem like almost a silly problem. But let's take a look at it in a little more detail. So let's take a look at name, for example. Couldn't we just match up the names of everybody in the state death records with the names of everyone in our EHR? Well, it's important to keep in mind that names can change. And of course, one very common example of this is many women changing their names after marriage, but there are other circumstances as well. And there's no guarantee that that name will be reported in the same way in both data sources. Similarly, some people will go by their middle name or go by a shortened form of their name, and that functionally becomes their first name. Again, it could end up getting reported differently in those two sources. Some people have more than 3 parts to their names. They don't fit nicely into those buckets. We have a first, middle, and last name. So what goes into the last name bucket or even the middle name bucket, again, could be different. And then there's always room for data entry errors as well. So anytime when we're going to have a human that has to type in a name or a number, they can misspell something, they can mix something up. You can particularly think about cases where someone has a last name that sounds a lot like a first name. We could see those get swapped in a particular record. So there's lots of ways in which name is not always going to provide a perfect way to line up two records. And I can hear some of you asking me or saying, well, I'm more intelligent than that, JP. I wouldn't have tried to use name. Shouldn't we be using social security number? Isn't that a better unique identifier that we could use to really line up one-to-one? And I would say, yes, usually it is. So we do like to use that as well, but it's not infallible. So we can have problems with misreporting even for something like social security number. So when you're thinking about what can happen here in these cases, it's important not to just think about the prototypical patient and the way things should work, but you have to try to think about those fringe cases. For example, we could have lots of patients at some stage of cognitive decline, or we could have a caregiver trying to administer the records for a given patient. Maybe the caregiver is in a state of cognitive decline as well. So there's lots of ways things can go wrong here. And one way we see in particular is sometimes we see the social security number for different family members actually will get swapped on occasion. Again, always possibility for data entry errors here as well. So it's not perfect. We could look at a similar breakdown for date of birth and other identifiers, but the takeaway here is there's no single identifier we have that can always be used to perfectly align records from two different data sources. So this leaves us with a balancing challenge. On the one side of this, if we set our matching criteria too strict, how we're going to try to match up all the identifiers we have from the two data sources, we're going to get too many false negative matches. And that's the case where we have a patient who has a death record, but we didn't find that match because we weren't allowing Larry to be Lawrence in the other data set, for example. On the other hand, if we set our matching criteria too liberally, we'll end up with too many false positive matches where we have matched a patient with a death record when that shouldn't have happened, maybe because that patient doesn't have a state death record or because we matched them with the wrong one. So we're left with this challenge here of trying to balance too strict with too liberal in our matching criteria and trying to minimize both false negative matches and false positive matches. So this is how we do that. This is our linkage approach that I will be walking you through here. And then I'm going to break down each of these steps in a little bit more detail in the next slides. So in the first step of our process, we're going to find a big pool of all the potential matches that we're going to examine. And we do that using three different linkage algorithms that I'll talk about. So we take the results of all of those, pull them together, and then we have all of these potential matches that we can consider. And then in the next step, we're going to feed those to a two-stage classification process. We're going to classify all of those potential matches as either positive or negative matches, or in other words, matches that we believe are correct or that we think are likely incorrect. And as I said, that's two stages. The first one involves us assigning a score to each potential match, and then applying a threshold there, eliminating all of the lowest confidence matches. And then in the second stage, we are running all the remaining ones through a machine learning classifier. And then once we get out all of the positive matches at the end, we can then save those as our final results. So let's dive into a little more detail on these. So first up, finding our pool of potential matches. So we experimented with a variety of linkage algorithms, and what we found was that the combination of these three specific ones that I'll talk about had good sensitivity for finding most of the positive matches that we want. So the first one of these algorithms is going to pull a potential match if there was an exact match on sex, last four digits of Social Security, and beginning of the last name. And what this algorithm is really accomplishing is finding the easy matches. So cases where they look like we would hope they would. Almost all the identifiers are looking very similar in both data sources. This algorithm will find those matches. On the other hand, the second algorithm starts the same way. So it looks for an exact match on sex and last 4 digits of social security. But this time it looks for last names that start differently. So what this one buys us is a chance to catch those matches that have some of those situations we talked about before, like the last name changed, or there's more than 3 parts to the name. So the last name field just doesn't contain quite the same information in both data sources. And then the third algorithm is a little different still. It looks for a full match on the social security number, but looks for first names that are different. Again, this can help us to catch those situations like someone going by their middle name or going by a shortened form of their name, and then that ending up being recorded differently in those 2 different systems. The other thing to keep in mind here is that we actually have 7 identifiers that we compare in total between the record sources. And none of these algorithms require an exact match on all of those. And because of that, each of these algorithms has some capacity to handle those misreporting and data entry errors that we talked about when just 1 or 2 characters get off maybe on a certain identifier. Okay, now you may ask me, JP, isn't it possible that more than one of these algorithms is going to produce the exact same match? Is that a problem? Do you have to deal with that? And what about when a single patient gets matched to more than 1 state death record? Or conversely, 1 death record gets linked to multiple patients? And I would say those are excellent questions. And yes, that's something we have to consider and deal with. This first one, though, is pretty easily dealt with at this stage. So as I said, we're going to take the potential matches we get from each of those 3 algorithms, and then we're going to pool them together. And when we do that, we deduplicate at that stage. So it doesn't matter if more than one of the algorithms picks up the same match. It's not going to result in any sort of duplicates in the final results. The other 2 points, though, are a little bit more tricky, and we're going to have to circle back to those later on. So at this point, we have that pool of potential matches we're going to consider. And as I said, we found that those 3 linkage algorithms together have good sensitivity in picking out the positive matches. But we can't stop at this point because their specificity is terrible, which is to say we have our positive matches now, but they're swimming in a sea of negative matches. So at least we have a more manageable pool, though, at this point of the potentials. So at this point, we can start to examine them more closely and then classify each one as positive or negative. So as I said, we've got a 2-stage process for this. And the first stage of this is scoring each one for the quality of that match. So we do that with what we call the weighted match score. So it's actually a combination of several component scores. So we're going to compare the 2 records. And as I said, we have 7 different identifiers we compare, and we get a score for how well each pair of identifiers matches up. So then we sum all those scores together, and we get this total weighted match score, which can range from -25 to 80. So -25 would mean every one of those 7 identifiers looks pretty different between the 2 records. Whereas if they all matched up perfectly, that would be a score of 80. So this process is known as probabilistic matching. And then once they all have a score, we simply apply a cutoff at 30. So every potential match that had a score below 30, we're going to go ahead and classify as a negative match. And that's based on manual review, where we get that 30 from. So I'll talk a little bit more about the manual review in a moment, but essentially somebody had to manually inspect and then classify a lot of these potential matches. And when they did that, there was never a case where a match got classified as positive that had a score less than 30. So we feel confident that we can go ahead and take all those less than 30 scores and call them negative matches. All right, so we've divided up our pool now. We've taken everything with scores in the lower part of the spectrum. We've said you're just not good enough, you have to go. But everything left in the upper part of the spectrum still has a chance, and it goes on to the next stage of the classification. And that's the machine learning classifier. So for those of you with some familiarity with machine learning algorithms, the specific algorithm that we're using here is a histogram-based gradient boosting tree classifier. So it's an ensemble model that uses decision trees as the individual base learners. And if you're familiar with the XGBoost package, or that's something that you've heard of, it's a very similar model to an XGBoost model. So the first thing we've got to do to get this classifier working is we have to train the machine learning model. So we have to give it a chance to learn how to distinguish between negative matches and positive matches based on the data. And to do that, we need to give it some data that already has the answers in it, that's already labeled as positive or negative matches. And where do we get that? From the manual review. So a poor dedicated soul had to carefully inspect and then classify about 1,400 potential matches. But the thing to keep in mind here is that actually most of the potential matches we get from those algorithms are either clearly positive or clearly negative. They have high weighted match scores or low weighted match scores. The more difficult cases with the mid-range scores are much less frequent. But these are the types of cases that it's especially important that we let the machine learning model learn how to classify well. So because of that, the training data set here is not a fully random sample, but instead we've actually oversampled for more difficult cases to classify, those with those mid-range scores. So we're doing that to give the model the best chance we can to learn how to handle the difficult cases. The other thing I want to talk about with the training here is that while all of these training cases do have a weighted match score, we know what that is, we don't give that to the model as a feature that it can learn from. And there's a few reasons why we don't do that. So one is that that weighted match score is largely more for us, the humans. So there's a lot of identifiers that have to be compared here. And it's easier for us humans than to find just one summary score that's going to kind of bring all those things together and just give us one easy number to tell, is this a strong match or a weak match? And the computer just doesn't need that. It's able to look at all of the individual data elements. The second part of it is the weighted part of the weighted match score, which is something we haven't talked about. But there's a lot of subjective decisions built into that score. So we've decided how much we want to count an exact match versus a small difference versus a big difference on Social Security number, how much that should contribute to the total score versus how much, little differences or big differences in first name should contribute to the total score. So those are the decisions we've made in building weighted match score. And there's no reason that we need to give those subjective decisions and build that into the model. So that's another reason. And the final one is just, what's my final one? Oh yeah, if we give the weighted match score to the model, even though it's got our sort of subjective decisions in it, it still is a summary of the overall matching of all the different identifiers. And because of that, the model will just latch onto that. It's going to focus on that and just ignore almost all the other data that we give it that it could use to make decisions. And that's not what we want. We want it to focus on all the element level data. So that's why we don't give weighted match score to the model. All right, so how good is this classification process? What's the performance look like? So this is what our performance looks like on our training data set using cross-validation. So this is the performance in terms of a confusion matrix. For those of you that like confusion matrices, if instead you prefer these more summary metrics like sensitivity and specificity, this is the exact same performance data just expressed in that format. And if you don't like either one, I'm sorry for bringing it up. But what we can see here is that sensitivity and specificity are both hovering around 90%. So another way to say that is that our false negative rate, that is how often we are missing a match between a patient and a state death record that we should be finding, about 0.7%. And our false positive rate, when we're matching patients with death records when we shouldn't be, is about 1.2%. And I note here that actual performance may be a little bit better. So why do I say that? So as I said, this is the performance on the training data set. And if you recall, we specifically designed the training data set to be more difficult than we expect the general population of data to be. So it's very possible that performance metrics could be a little different and potentially a little higher or a little better for the population of data. All right, so at this stage, we have applied our two-stage classification to all the potential matches. They've all been classified negative or positive. We're going to drop all the negatives and we keep all of the positive matches, which this is something that we run over and over again with our data. But at this point, it's about 500,000 positive matches that we get from the state death records. But we're not quite done yet. We've got one more wrinkle that we do need to iron out, and that's dealing with multiple match cases, which is something I said we were going to circle back to. So at this point, it turns out we have about 0.04% of patients that have multiple positive matches with the state records. And I say multiple, it's almost always two. So one patient gets matched with two state death records. So we manually inspected these cases to see what was going on. And it turns out that in most of these cases, it's pretty obvious which match is likely to be a true match and which one is likely a bad match. And the true match generally has a weighted match score that's much higher. It just looks like a much better match. So we're able to deal with a lot of these pretty simply by retaining the match that has the higher score. So that takes care of a lot of these. And then out of the remaining ones, we looked at those and we saw that in those cases, they have ties at this point on weighted match score. So it really looks like the same person got two state death records that looked almost the same for some reason, except one of those records is missing the death data and the other one has it in it. So the death data being like date of death and causes of death. So not sure why that happens, but again, it's pretty easy for us to deal with those exceptions when it does. When we see that, we just retain the record that has the death data filled in and drop the one where it's missing. So after those steps, we've reduced this down to 0.001% of patients that still have multiple matches. Now, these ones we don't have a way to automatically resolve, unfortunately, so they do make it into the final results. But because the number is so small, you're not likely to encounter it. What it looks like is happening here, though, is, again, a patient has two records, or the same person has two state death records for some reason, and they both have death data in them, but usually the death data are like ordered a little differently. So they list multiple causes of death, and for some reason, the order of those causes of death is different between the two records. Now, if you're a researcher that just needs to know, is this patient dead or not, this isn't even a problem for you. It's only if you're interested in the very specific causes of death, but the number is so small, it could also probably be dropped. All right, so now we have reached the end. We got to our final positive matches, and we will save those into a table that can be used for research purposes. So this table gets updated on a monthly basis because that's how often we receive new state death data. And it includes things like I've said, the date of death, primary cause of death, any other recorded causes of death that were in the state record, And the weighted match score is accessible in this table as well. So if you have a research project, how are you going to access these data? So I'm glad you asked. TRACS has a standard procedure for provisioning EHR data to researchers. So if you are a UNC researcher or you're collaborating with a UNC researcher and you have an IRB protocol giving you approval for the specific data that you're trying to use, you can go to the TRACS website and click on the button to submit a data request. And at that point, the TRACS staff will guide you through the rest of this procedure for getting access to the data that you would need. And those types of requests that involve mortality data now have the option of accessing the results of this linkage process that we've talked about today. Okay, so we've accomplished our goal here. We were able to fill in a lot of that missing death data that was in the EHR. And we feel good about the solution that we've developed. But the last thing I do want to mention is that technically we're not the only game in town. So it turns out that UNC Health has a process that's been developed independently from ours for doing this same type of state death data linkage. And this is managed by their Information Services Division. So this other process is using the same state death data that we are, but it differs a little. It applies a more basic linkage algorithm that comes built into Epic, which is our EHR software system. And we were able to look at their process a little bit more closely and see how it works. We ended up deciding that we wanted to continue using this process that we have developed. And there's a few reasons for that, but a couple of those are that this Epic process currently just matches state death records from 2022 onward, whereas our process is matching all of the state death records that we have access to, which go from 2010 onward. Another difference is that with the Epic process, we just don't have any data about its performance. So we don't know about its false positive rate and false negative rate. Whereas we have been able to run some validation analyses on our process, which do suggest very good performance. Now, a little while back, we also ran sort of a quick course comparison between the two processes by comparing the positive matches that we got out of each over the same 19-month period. And when we do that, we see 50,000 positive matches coming out of the Epic process versus 73,000 coming out of our process, with about 45,000 of those overlapping. Now, again, we can't speak to the breakdown of false positives versus true positives in the Epic results in particular here, because we just don't have that data. But another way to look at these is that our process is capturing 91% of the positive matches that come out of the Epic process. And the Epic process is capturing about 62% of the positive matches that come out of our process. So all of this is to say, we do feel confident in the linkage process that we've developed, and we are planning to continue using it in TRACS moving forward. So with that, thank you all for your attention, and I'm going to open it up to any questions.
I have a couple of questions, actually.
Yeah.
With the probabilistic matching and the machine learning classifier, are you keeping the date of birth as 3 separate components?
I guess I'll repeat it for the Zoom just in case. So the question was, when we're doing our linkage, do we divide up date of birth into the different date components, or do we just keep it together as one whole element? And the answer there is we do keep it as one whole element. But part of the way we do our linkage does rely on a scoring procedure called Levenstein distance. And that looks at how many character changes you would have to make to get from one value to another. So if 2 different dates of birth are only off by 1 day, it doesn't really matter like which part of it it's in. it'll get scored in a
Does
similar
it
way.
allow for like a fuzzy match where like the month maybe matches in the year, but not the day? Or the day maybe matches, but not the month, the day and the year?
Yeah, so it can find those sorts of partial matches and they'll just be scored a little differently depending on how many pieces are different.
Mhm.
I think it's been a long time since my hands have actually touched this code. So I originally wrote this code like the original version of this code like 10 years ago, and it's gotten updated and updated. But I'm pretty sure from the start, I treated date of birth as both character and numeric, specifically for that purpose. So it was not broken into 3 separate components, but keeping it as character allowed you to look at differences in a different way, even than looking at it numerically. I was interested in both, like, what are the potential like input or character differences, even versus like what are the day difference issues. It's different versions of those manifested in different records.
The other thought I had was just about like, well, this is sort of 2 pieces, like you talk about like these duplicate data, like maybe they have 2 records, but one thing that you didn't mention was fraud. And there is like, and I don't know how much, I mean, when I was in California, we had to think about that a lot more because there's way more people, but there is like Social Security fraud. So it may be if you have like someone dead twice, it could be that you've got like maybe a Social Security number that's being like used fraudulently.
Yeah.
Do you want to speak to it? Do you want me to speak to it?
I'll let you go ahead and speak to it. I just said it. I think my mic's probably picking you up, so I'm not gonna go ahead and repeat it, but yeah, go ahead, Peter.
Yeah, so it's something that's a fairly complicated question. And it's complicated both because it's on the input side with Epic, as well as for us on the backend side. And what's interesting is, again, as I've looked at this over, like 10-ish years, it doesn't really look to me like there are a ton of input or check controls on the actual registration side of Epic. Because what you find is just, easy places that you can start it out with, right? So like patient table and clarity. How many times is a unique, like, or what I should say is a full like 9-digit social security number duplicated, right? Because you also don't have to actually, well, a social security number is required. You don't actually have to put in like 9 digits. Lots of people put in 000000000, right? Or just the last 4 or a variety of different things. But if you look at a place where they actually have all 9 entered, like you find dozens of people with the same social security numbers. But again, like from our perspective, like the fraud piece is not like there's operationally like nothing that I could do with that. That would be like an Epic and a registration question, but it is something we have to account for, obviously, because I mean, both it could be happening intentionally, and it also clearly happens unintentionally often. That happens with social security number. It clearly happens with date of birth. It happens with, like address. Address is used as part of the match criteria. So like what your numerical address is, as well as, portions of the strings of your street address, like the street name. And so, like what you say, or at least what I saw over many years, is like fat fingering or just misremembering this data is like incredibly possible. Not only that, but just even the ability to like randomly get one of the digits of your 9-digit social security number wrong is like reasonably good. And so, yeah, I mean, pretty much all of these elements are fuzzy matched. But yes, like once I sort of saw like, oh, the same social security number is duplicated like many, many times, I think that is a concern. But it's just like, that's on the, what is it? The HIM, like health information management side for the healthcare system.
Well, I was just thinking maybe as a researcher, if there were like, maybe I would want to know if the patient had like multiple death records. Maybe I'm not going to trust that as much because that could be like a social security. That would be the only point. I know there's no way to prevent it.
Yeah, I mean, it again, it depends on what the definition of a duplicate record is, because there are lots of, records that sort of meet a definition of duplicate, but it's because, the elements are close enough to hit below like a a probability of being a non-match. But that's really different than like being a very high confidence, high probability match and also being duplicated. Like that is
That's
significantly
smart,
low.
I mean, yeah.
Yeah. Mhm.
And then people who live out of state, do you recommend that you only do this, like, do you only do this for people who have an in-state address in Epic?
So that is, I've never really gotten a straight answer from the North Carolina DHHS about that. I mean, so this is their death certificate system, which they have to keep, right, for vital status records. But then also, this is their input into the NDI. And the thing that I have never totally been able to figure out is, are they generating death certificates for, the closest I should say is, my understanding is, it's for people that die in the state of North Carolina, right? So if you came from Virginia to UNC Health Center and died, you would get a North Carolina death certificate. If you were from Chapel Hill and went to UVA for healthcare and died, you would not get a North Carolina death certificate, is my understanding. But I have never had someone definitively say, yes, that is 100% true 100% of the time.
Sure,
Hi, sorry, this is,
if someone, but, so like in the western part of the state, and I'm still getting familiar with the UNC Health, but the western part of the state touches like 5 other states or something, right? So you could be a Tennessee resident who comes to UNC Health for your healthcare and thus are included in some research study because you touched UNC Health, but then you're in Tennessee when you die. And so we would have like no record of the death at all.
I mean, from again, the amount of information I've gotten is if you died in the state of North Carolina, then we would have you. But even if you were a UNC patient, but you died in the state of Tennessee, then we would not.
Yeah, yeah. So like we wouldn't know, you wouldn't have necessarily have confidence that you would capture all the deaths of patients who reside outside the state, right?
I believe
Yeah.
that's true. Yeah. Mhm.
I was trying to catch up on the chat a little bit, seeing if there are questions we've missed. One question was, are these data available to honest brokers? So yes, they are available to the honest brokers that do the data provisioning process within Trax. Another question was, what criteria or data were used for scoring? So I just started touching a little bit on that during the Q&A. So we had 7 different identifiers that we compared. Those are first name, middle name, last name, social security number, date of birth, street address, and zip code. And for each one of those, we derived that Levenstein distance, where we see how many character differences are there between the values from the 2 data sources. And that's largely the data that then gets fed into, well, it gets used to create the weighted match score and also gets fed into the machine learning classifier. Another question was, are there any geographic data available in the data sources? So I may not be answering specifically what you're asking. So, I mean, there is address information available in both data sources. So as I just said, we do use that in the matching process. And then independently of that, Trax has been developing some geodata that can be linked and provisioned along with EHR data in certain cases.
Maybe name place of death.
Yeah, my read was like what geographic data is available in the state death data, which I don't actually recall what we got.
Yeah, so in the state death data that we get, again, we've got an address for the person, but as far as the death data go, it's just the date of death, and the causes of death are the only elements that make it into our final results at this point.
So is there any cross linkage between middle and last and first names?
They all get scored independently, essentially.
Okay.
So the only way that they could end up being used together would be if the machine learning model decides to interpret them in that way.
That's interesting. I was thinking of, I've seen this with my grandmother's old records, so she had a middle name that was surname and then, yeah, so she basically had, and then she got divorced, so she basically had records that had any combination of 2 out of the 3 surnames in some order.
Mhm.
So it was very obvious on looking, but without cross-linking, it'd be hard to connect some of those.
I see, yeah, so we don't have a specific way to find if middle name and last name got swapped, for example. We'd just be relying on those different algorithms that essentially allow a different middle name or a different last name to pick up that match, and then it would get scored accordingly down the line.
Did
Yeah.
you find in,
Oh.
did you find in your tough cases that there were a lot of non-Western names? Because I know that names are structured differently all over the world, right? And my hypothesis would be that a lot of the matches that we do less well on are names that, kind of like you were saying, don't fit neatly into those buckets, or did you not see a pattern?
Yeah, Peter's probably the better one to speak to that because he examined more of these individually.
My experience is actually the opposite. Because those names are relatively unique in the population of names that we have, they're almost easier to match. Yeah, the one difficulty with that might be cultures where hyphenating multiple names together is complicated. Because you'll have like 4 or 5 names, like hyphen, 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 hyphen. And the only reason that is complicated is the parsing of it logistically, because they're one or, it's a very small proportion of names. And so it's trying to account for that, construction out of the like 2 million other names you're working for, right? So like those admittedly don't get handled as well. But I mean, otherwise, yeah, truly, because the names are so rare, I feel like they almost match with higher confidence.
Abby.
From a population level standpoint, do you have a rough estimate as to what proportion of state deaths are captured in EHR data?
Let's see.
Do you mean like if you're able to somehow union all health centers together?
Right, or just sort of within the UNC health system or the data set that you have. EHR data has a lot more information on an individual level basis, especially in terms of like quantifying different determinants of health, etc. I think it would be like as a different source of data for somebody interested in mortality research.
Yeah, that's an interesting number that we could probably find. I don't have the access to do it myself, but I could certainly team up with somebody else in tracks. So we don't know that number right now, which is how many deaths does the EHR capture on its own without us doing the supplementing process. But yeah, so that's probably something, a number we could get and then report later on.
And do you mean like that the context of the death is captured in the EHR, like the circumstances that led to the death and all the interventions, or just the fact that the death's there?
Just that that's there or not.
But isn't that what this does? It adds that to the.
Yeah, I mean, so that's what I was gonna say. I mean, we already know that the deaths represented in EHRs are far, I don't know what adjective to use, but definitely underrepresent the number of actual deaths. Because just even by linking UNC's EHR data to state level data, you get an incremental 500,000. Is that right?
It's not 500,000 more, it's 500,000
Total, yeah.
It'll be acute deaths too, like think about the kind of patients who die in the hospital, like are the acute deaths that are coming from, like if someone's moving towards death, UNC will send them somewhere else, like palliative care, hospice or something, so.
Largely,
Yeah.
I mean, there are still more than acute deaths. And there's a very, very small portion that do get picked up and manually added. But I mean, my understanding is that those are truly like we called someone to collect a bill and
Mhm.
their son told me they're dead.
Is it on the
And we have to update the
in
record.
the HIE?
I have never been able to confirm that. Ever since I started this work, I sort of wondered why the HIE didn't do this at a state level and sort of make it available as a service. But admittedly, I've never really been able to understand like the operational service that the HIE serves in North Carolina. Yeah, I mean, this because I feel like, I mean, we're working on, like, we're in a situation now where every health center sort of needs to attempt to solve this on their own. Which some places are capable of doing and some places contract, you know, to do. But I mean, it does seem like the type of problem that you would want something like a statewide HIE to solve, rather than everyone sort of solving it over and over again on their own.
Mhm.
I've been surprised too. I sort of assumed that everywhere that this was not sort of like new or novel work for a long time. But as I met people from other academic medical centers, what I found is lots of places either struggled with this or sort of came to a similar solution that we had. Like they somehow amassed some sort of localized external death data to match to their data if they were capable of doing it. But that this was like this was not a solved problem in lots of places, which was a surprise to me. Because this seems like such a really basic, fundamental sort of data element to have for research.
Answer the question on the chat.
Yeah, this has been great and lively conversation. I know we're coming up on time before too long, but are there any other questions either in the room or I know the chat has been lively. I don't know that we've been able to keep with everything there. But is there anything else there that we should come back to?
There's one question in the chat I wanted to address, which is if we have a publicly available code repo with this code. And we do not yet, but I think we could share the code that we use here. Of course, we can't share the actual source data files that we're using, but if you're just interested in the linkage code itself, yeah, I think we can probably make that openly available soon.
Yeah, we have the IDSci public GitHub repo. It'd be great to have this as a project under that organization.
Okay. Yes, we did hear recently about the Shep Center has a related linkage process as well. Although it sounded like it hadn't maybe been implemented on as large a scale, maybe it was more for individual studies.
Sounded like it was for one study.
For one study.
For Inspire, but it sounded like that was the extent of it.
But yeah, I don't have a lot of information on that.
Yeah, and it looks like there's a question about table names for CDWH3. We don't use CDWH3 in HANA, so I think those would be questions for ISD. Oh, there's someone else who could answer this question better. So I was mentioning in the chat how the results that we're generating are not being added to the Epic EHR records themselves. They're being kept in the separate research table right now, which can only be accessed through data requests through tracks. There was a question about whether the ISD process that I talked about at the end, whether those results are in the EHR. And I don't know enough about how the data exists there to answer that in detail. So they do get updated in a clarity table, but I don't think that's something that's just generally accessible in Epic. That's something we can access through tracks, those results again. So we do have access to their results. Yeah, I'm not even 100% sure what their process is at this point, because like within the Clarity patient table, I know there's at least one or more columns for death. And I'm not sure what data might be getting populated into which column. And so like I think you would want to check with ISD on like where their matched score is going and those types of things.
Yeah, I know that the Clarity table it goes into, it doesn't contain almost any data. It's just a date of death, I think, is the only death data.
But there's the date of death that's recorded in Epic. And then I think there's another column for a matched date of death, is there not?
Yeah, I think that's right.
Yeah.
But I
But
don't
know
think,
which of those as well.
I don't think causes of death are getting populated in this Clarity table from the state death records.
No, I don't believe any state death data. I'm not sure that any state death data is getting used to really populate any of this information at this point, right? Like, I don't think they're bringing in like any of the basically like death metadata that you get from the state death files.
Thank you.
Right.
That's really helpful because we had heard
As a
that.
researcher, if I want to use these data, do I have to go through a process whereby my research protocol gets reviewed by the HHS?
No.
Okay.
Yeah, no, they're made available to us for research purposes, so,
For reuse.
I mean, you could not then, reuse them,
But you can.
provide them, correct,
Okay.
yeah.
So,
Thank you for clarifying.
so
We can reuse them to give to you, you could not reuse them to
Yeah,
then
thank you.
serve to someone else.
last I heard, when a researcher makes a request that are going to use these results, there's like one extra form that gets filled out that then goes back to HHS that says, they got used in this way. So it's not like something that gets reviewed,
Not
it's more just
pre-approval.
for record keeping, yeah.
It gets overstated.
Yeah, the state has been very helpful and supportive. They are, as you can imagine, they are not resourced amazingly well, but they are very helpful and supportive of like all the things that we tried to do with us at UNC, which has been great and very helpful.
So I do want to say thank you to everyone in the chat for all of the contributions here. And if I missed your question here, do feel free to get in touch with us here, and you can use my email address on the slide here.
Well, so there was a question that may have just come directly to me about how would an honest broker see this data? I think the best thing to do is to talk with your contacts in the EHR data team, because this is going to live as a custom table in the track schema in Cloud. So, depending on what resources someone is used to working with, it may or may not be straightforward. And additionally, I think the EHR data team wants to make sure that people are sort of well acquainted with the different cutoffs and different metadata that can be used in the table, just to make sure that everyone is kind of using it in a similar way. And with that, I see that we're at time. So I will also thank everyone for attending and supporting us. I'll be sending out information on our March Data Science Lab seminar, within the next, I don't know, a couple of days, maybe within a week. And similarly, once I get the recording for this posted on the SharePoint site, I'll let everyone know about that too. All right. Thank you.